Hello, hi students. We are looking at nuclear magnetic resonance spectroscopy. In the previous sections, we have seen equivalent and non-equivalent protons and calculation of number of signals from a given compound or a sample. In this lecture, we are going to see your reference compound or reference signal obtained from TMS and NMR splitting of signals. How singlet, doublet, triplet signals are obtained, which is calculated as a multiplicity of signal, and other one is spin-spin interaction, which is given as J coupling or spin-spin coupling. Let us see these things from the lecture. In NMR, we get a zero signal at for tetramethylsilane. For tetramethylsilane, we get signal at 0, or the line that is obtained for tetramethylsilane is taken as reference line, or it is taken as 0. So the signal for tetramethylsilane comes upfield to most of the hydrogens in carbon compounds. In tetramethylsilane, the 12 hydrogens of the silane are chemically equivalent or in magnetically same environment. Because of the similar environment, these 12 hydrogens will give a sharp line upfield to all other hydrogens of carbon compounds. Therefore, this tetramethylsilane is the established standard, or it is taken as internal reference compound for H1 NMR or proton NMR. This tetramethylsilane will give a strong and sharp line from its 12 protons. So put together we have 12 protons in tetramethylsilane: CH3, CH3, CH3 and CH3. 4 CH3s are there. So in total it is 12 protons. All 12 protons are chemically equivalent. Therefore, it gives a very sharp and strong resonance line and comes very much upfield to any other hydrogen in carbon compounds. Therefore, it is taken as a reference line, and your carbon compound is usually, before sending for NMR, this tetramethylsilane is added to the compound, so that you will get a zero line or reference line you will get. Therefore, that 12 hydrogens signal is coming at a very low value relative to almost all other hydrogens of different compounds. Hence, this is taken as zero line or a reference line. And it is pretty much easy to remove this tetramethylsilane from our compound or sample, because it is highly volatile. This tetramethylsilane is highly volatile and easily evaporated, and do not react, and tetramethylsilane is mostly inert and do not interfere with our compound under investigation. Whatever compound that we are trying to elucidate, that compound can be easily extracted back, because it won't interact with that compound owing to its inertness. Inertness means it won't react much, or it doesn't react, or it do not interfere with our compound. Hence what you can say is that it is easily volatile and not interacting with compound, so can be used as a reference. And highly soluble also, it's easily miscible with organic solvents. With the known solvents, it is easily miscible. When an organic compound is dissolved in organic solvents, in any of the given organic solvents, this tetramethylsilane is soluble. Hence it is very much desirable to have tetramethylsilane as, or TMS, as what, a reference compound. And this comes very much upfield, the signal of these 12 protons, and will come very much upfield, and because of having 12, quantum of that protons is also 12, amount of that protons is also high, the number of protons is also more, so you'll get a very sharp line, and a sharp line you'll get upfield. So that is taken as what, zero line it is taken as, so hence it is considered as a reference. So that's the information of your tetramethylsilane, and why it is established as internal reference. Okay, so someone asks you a question that what is TMS and why it is taken as a reference compound in NMR, that you can write something like this. Okay, so that's your answer. Now let us see splitting of signals, splitting of NMR signals. So what is the splitting of signal? So once someone said that you will get 3 signals or 4 signals, and if you minutely observe that, microscopically observe each signal, that internally splits into 2 lines or maybe 3 lines, sometimes 4 lines, sometimes 5 lines also. Each signal, if you observe microscopically, you can notice splitting of signal, that is, it splits into 2 lines or maybe 3 lines or maybe 4 lines, like that. So a signal in NMR represents characteristic protons, given a set of protons, and these signals, if observed microscopically, instead of being one single line, there is a chance of having more than one single line. That is called as splitting of signal. This splitting of signal is based on the number of adjacent protons. Here adjacent refers to hydrogens present on adjacent carbon atom. So if a line is splitting into 2 lines, if a signal is splitting into 2 lines, we call that one as a doublet. So for example, if you could see some signal, that signal is split into 2 lines when observed microscopically or when noticed microscopically, or on resolution, you can see the single line splitting into what, 2 lines, and then we classify that line as a doublet peak or a doublet signal, we call that one as. If you got a doublet, which means the adjacent carbon is carrying 1 proton or 1 hydrogen. Similarly, if certain signal is split into 3 lines on resolution, if you could see 3 lines in that, then we call that line as a triplet. Our signal is a triplet. When we get a triplet, if adjacent carbon is having, or carbons are having 2 protons, then we get a triplet. Similarly, when a signal is seen as a quartet, 4 lines, when a signal, one signal is on resolution, if it is appearing like a quartet is a 4 lines, which means that the adjacent carbon is having 3 protons. Adjacent carbons are carrying 3 protons. So just to understand that, we have color coded the protons, sets of protons we have color coded. So let us see that blue hydrogens and red hydrogens, I have classified them as. Blue is adjacent to red, red is adjacent to blue. So number of red hydrogens will give the signal corresponding to blue hydrogens, and number of blue hydrogens will give the signal corresponding to red hydrogens. We should check vice versa. That is, blue hydrogens for the signal of red hydrogens and red hydrogens for the signal of blue hydrogens. So if you want to know the signal of a red hydrogen, what we should check? You should check the blue hydrogens number. And if you want to know the number signal of a blue hydrogen, you should check what? Red hydrogens number. So based on the number of red hydrogens, you will get the signal of blue hydrogens. Based on the number of blue hydrogens, you will get the signal of red hydrogens as something like this. The multiplicity of a peak is given as n plus 1, where n is the number of adjacent hydrogens on adjacent carbon. So if blue hydrogens are 2, you will get the red hydrogen signal as 2 plus 1. If blue hydrogens are 1, you will get the signal of red hydrogens as 1 plus 1. That's what we have just seen as that a triplet if 2 protons are present on adjacent carbon, a quartet if 3 protons are present on adjacent carbon. So the formula is given as n plus 1. Multiplicity of the peak is given as n plus 1, where n is the number of adjacent hydrogens. So just to see that, so this is summary of signal splitting pattern in NMR spectroscopy, H1 NMR spectroscopy. The pattern is that if n protons split the signal into n plus 1 peaks, which is known as n plus 1 rule. So your multiplicity is given as a doublet peak for n plus 1, that is 1 plus 1. So if you got a doublet, means adjacent carbon is carrying what? 1 hydrogen. So 1 plus 1 is 2. So your signal you can expect as a doublet, something like this. So you can see this is a doublet peak, 2 lines. It is a single signal which is on resolution observed as a 2 peaks. A single signal which is obtained as 2 peaks, so it's a doublet line. So which means that if you are going for red hydrogen signal, is based on blue hydrogens. So which means how many blue hydrogens are there? 1. So 1 plus 1 is 2. So you'll get a doublet for red hydrogens. And what about blue hydrogens? For blue hydrogens also you'll get a doublet, because how many number of red hydrogens are there? 1. So which means 1 plus 1 is equal to 2. The formula is n plus 1. So number of red hydrogens plus 1 is equal to 2. So you'll get a multiplicity of the peak as doublet, which is shown as small d. So let us see that one in the case of some other. For example, this is the compound. This is your compound which is having red hydrogen 1 and blue hydrogens are 2. If blue hydrogens are 2 and red hydrogens are 1, so how is the red hydrogen signal expected as? Red hydrogen signal is based on adjacent carbon's hydrogens. So adjacent carbon is carrying 2 hydrogens, that are blue hydrogens. So 2 plus 1 is equal to 3. The formula is n plus 1. So 2 plus 1 is equal to 3. So your red hydrogen gives a signal something like this, which is a triplet, 3 lines, 1, 2, 3 lines. So therefore it's a triplet. What about the blue hydrogen signal will be like? Your blue hydrogens are chemically different from the red hydrogens. So the blue hydrogens will give a signal something like this, a doublet. Why a doublet? Because the number of red hydrogens is 1. So 1 plus 1 is 2. So for the signal of blue hydrogens, we should count the number of red hydrogens. So how many red hydrogens? 1. So 1 plus 1 is equal to 2. The formula is n plus 1. So we'll get a doublet. Similarly, some other example have a look at. Well, in this case of this, so this is your compound. So you have 2 red hydrogens and 2 blue hydrogens, and the chemical environment of these red hydrogens is different from the chemical environment of these blue hydrogens. Then in that case, the red hydrogens are obtained as a signal something like this, 2 plus 1, because blue hydrogens are 2. So 2 plus 1 is 3. So you'll get a triplet, which is represented as small t. And similarly, for the signal of blue hydrogens this way it is. So how many red hydrogens are there? 2. So 2, and the formula is 2 plus 1, n plus 1 multiplicity rule is obtained. So you will get a triplet. So both hydrogens, red hydrogens and blue hydrogens, will give you a triplet signal. Triplet and triplet. At what point? That depends on the compound. at what chemical shift value. And quartet, so just to give quartet, how, for example, look at the red hydrogen. So red hydrogen is 1, but blue hydrogens are 3. So the signal of red hydrogen is obtained based on what? Number of adjacent carbons hydrogens, number of adjacent hydrogens. So how many adjacent hydrogens are there? 3 adjacent hydrogens are there. Blue hydrogens are 3. Therefore your signal will be like a n plus 1, that is 3 plus 1. So 3 plus 1 is a 4. Therefore you will get a quartet. Quartet means 4 lines. 4 lines are also something like this. It has to be like this, not 4 equal lines. And similarly, what about blue hydrogens? The blue hydrogens in the last compound. So in the blue hydrogens here will give you a signal corresponding to what? Adjacent hydrogens. How many red hydrogens are there? 1. So 1 plus 1 is a 2. So the signal of blue hydrogens will be a doublet, and the signal of red hydrogen will be a quartet. Got it? So that's how you calculate the multiplicity in the case of hydrogens. So the pattern is based on n protons. Split the signal into n plus 1 peaks. If you have n adjacent protons, you will get signal as n plus 1 peak, which is known as n plus 1 rule. So let us see that one in the case of ethyl chloride. So how would you get in ethyl chloride? How many types of protons? 2 types of protons are there. This is CH3, CH2, Cl. So CH3 is different from CH2 set. Therefore, how many signals you will get? You will get 2 signals. You will get. If you are getting 2 signals, we are getting 2 signals. So what are those? For ethyl chloride, 2 types of protons are present. Hence 2 signals. So one is a quartet and another one is a triplet. How a quartet? Because this one will give you, the red hydrogens will give you a triplet, because blue hydrogens are 2, and the blue hydrogens will give you a quartet because the red hydrogens are 3. So 3 plus 1 rule, and here it is 2 plus 1, n plus 1 rule. By following n plus 1 rule, you can say that the methyl will give you a triplet and CH2 will give you a quartet. CH2 will give you a quartet in ethyl chloride. So similarly, in the case of ethyl bromide, here how many types of protons? 2 types of protons. One is CH3, another one is a CH2. The chemical environment of CH3 is different from chemical environment of CH2. So therefore, CH3 will give you a different signal and CH2 will give you a different signal. So you'll get 2 signals here in this case, and one is a quartet, another one is a triplet. Which is a quartet? CH2 signal is a quartet and CH3 signal is a triplet, because CH3 signal is dependent on CH2 and CH2 signal is dependent on CH3. That your CH2 adjacent hydrogens are 3, therefore a quartet. CH3 adjacent hydrogens are 2, therefore a triplet, by following n plus 1 rule. And quartet in short is Q, triplet in short is a T, small t. Singlet is S, doublet is D. Ethyl alcohol. So in the case of ethyl alcohol, so how will you get the signal? How many types of hydrogens are there? CH3, CH2, OH. Blue hydrogen, red hydrogen, brickish red I have given for OH. So you will get 3 signals as expected. So CH3 will be a triplet, CH2 will be a quartet, and OH will be a triplet again. But usually the signal of OH is not obtained based on the solvent. If you change the solvent, if you make use of water as a solvent, you won't get that OH signal. You'll get only 2 signals. One is a quartet, another one is a triplet. OH signal is not obtained. It depends on again the solvent that we are making use of. OH, this hydrogen is abstracted by water, H2O obtained as H3O plus. So you'll get CH3 CH2O minus in the sample. But anyway, for our sake, for current topic wise, you will get 3 signals. CH3 signal will be a triplet, CH2 signal will be a quartet, and OH signal will be a triplet. In the case of acetaldehyde, in acetaldehyde, so you have CH3CHO. This CH3 is in different environment to that of hydrogen on aldehyde CHO. Therefore, you will get how many signals? 2 signals you will get. And CH3 signal is a doublet, and CHO, this hydrogen signal, will be a quartet. Blue hydrogen will give you a quartet, and red hydrogen will give you a doublet, because blue hydrogens are 1, therefore red signal will be a doublet. And here in the case of this, your red hydrogens are 3, therefore your blue hydrogen will give you a signal corresponding to quartet, that is 3 plus 1 rule, n plus 1 rule. Okay, so that's how your acetaldehyde will give you a quartet of signal. Ethyl acetate. Look at the formula of ethyl acetate. So what is the formula of ethyl acetate? CH3CO O C2H5. CH3 C double bond O O C2H5. That C2H5 we write as CH2 and CH3. So therefore, based on the colors, you just identify the number of sets of protons. It is 3 sets of protons, or 3 non-equivalent sets of protons are there. Blue hydrogens, yellow hydrogens, and another one is red hydrogens, I can say. So which one will give you what type of signal? The blue hydrogens will give you a singlet, because there are no adjacent hydrogens, so you will get a singlet. These blue hydrogens, there are no adjacent hydrogens. See, this CH3CO, therefore this CH3 will give you a singlet, a single peak you will get. And what about yellow hydrogen? CH2 is in different environment to that of CH3 and this CH3, therefore this gives a different signal, and this CH2 will give you a quartet, because adjacent hydrogens are 3, red hydrogens are 3, and these are not adjacent hydrogens because these are far away. This CH2 O CO CH3, these are not adjacent. Blue hydrogens are not adjacent hydrogens, only the red hydrogens are adjacent for CH2, therefore it will give you a quartet. Adjacent means immediate carbon, immediate atoms hydrogens. So similarly this CH3 having adjacent hydrogens are what? 2, therefore you will get a triplet. This is a triplet of signal, quartet and a singlet. Therefore you will get 3 different sets which are non-equivalent sets of protons. Therefore you will get 3 signals. One signal singlet, another one is a quartet, another one is a triplet. So this is the splitting of a signal by following what rule? N plus 1 rule in the case of ethyl acetate. So by now we could understand what are chemically non-equivalent protons and the number of signals that a certain proton will be obtained as. So this is given in terms of spin-spin coupling. The splitting of signal is given as a spin-spin coupling or J coupling. This magnetically active nuclei, that is hydrogen, are hydrogen-like atoms which are having odd mass or odd atomic number. These magnetically active nuclei interact between them in terms of their spin-only magnetic moment. When these magnetically active nuclei are interacting, interacting means what will interact there? Their spin-only magnetic moment will interact, and on interaction it leads to a coupling that is called as coupling of the spin, called as spin-only magnetic moment will couple or will enhance. This is called as spin-spin coupling. So the magnetic interaction between the spin-spin magnetic moments of different nuclei is called spin-spin coupling or J coupling. In NMR spectroscopy, it gives rise to the multiplets of peaks. Just now we have calculated the multiplets of peaks, and because of this spin-spin coupling, spin-only magnetic moments of adjacent protons couple. When it couples, it leads to a phenomena that is called as multiplicity of peaks. Just in this case of a hydrogen, this a hydrogen is giving a singlet because there are no adjacent hydrogens to couple. But whereas in the second part of the picture, this a hydrogen is having one adjacent hydrogen. When the spin magnetic moment of this adjacent Hb hydrogen is interacted with the spin magnetic momentum of Ha, it leads to spin-spin coupling. The magnetic moments are simply coupled. Then the signal is obtained as a doublet, a peak, something like the signal is obtained as a couplet. And this is called as spin-spin coupling. So when you look at the Ha proton, if no adjacent protons are present, we got a singlet. We usually get a signal that is singlet. While in the second part of the picture, you have seen there is an adjacent hydrogen. There is an adjacent hydrogen. If you have adjacent hydrogen, if you have this adjacent hydrogen, then what happens is this hydrogen spin will couple with this hydrogen and results in a peak that is a doublet. So that's how here we got a singlet and here we got a doublet. Hence we can sum up that by looking at hydrogens, if no adjacent protons are present, we get a singlet, while presence of adjacent hydrogens produces a doublet. If one hydrogen is present, we got a doublet. If two hydrogens are present, we get a triplet. And this is due to magnetic interaction called spin-spin coupling interaction, represented by Z. Thank you.